Okay, so this is part two of lesson 13. Before I go on to parallel circuits, wanted to mention one more thing with series. So series circuits are your really old Christmas lights, where if one bulb breaks, then all the other light bulbs turn off. So found a GIF that kind of illustrates that point. So just talking about sort of if this resistor was broken, the electricity from the battery would get to this point, and it couldn't go any further. So the circuit would sort of cut off, and it wouldn't be able to work. So that's what would happen there, and that's why all these lights turn off when one is broken or one gets unscrewed. So that's a series circuit. And in a parallel circuit, it's different. So most of the time, your wiring in your house or wherever is in parallel. So if you look at this setup, you got your light bulbs, they're all lit up, they're all independent paths. So if I unscrew one, the other ones still work. It's not, they're not all dependent upon one another. So parallel circuits have more than one path. So this is a parallel circuit diagram here. So this is the total current leaving our battery. And the total current is leaving the battery in green here, and it makes its way to this point, which I'm going to use a special thing. So if I put the smiley face there and here, those are called junctions. So a junction is just a point where electricity can split or come back together. So the green current that gets to this smiley face is going to split up into two types or two different amounts. So it's hard to see the yellow, so I'll trace it. So there's a yellow current, which I'm tracing now in black, is going that way, and this would be I2. So that's the current that goes through that resistor. And then the blue current would be the current that came this way along the path and then went through here. This would be I1 because it goes through resistor 1. When they come back together, I1 and I2 should get you back to the total current that left the battery. So this is Kirchhoff's what's called junction rule. So we did a loop rule last time. This is a junction rule. So at a junction, the sum of the entering currents should equal the sum of the exiting currents. So whatever comes in should come out. So if you imagine this was 3 amps of current total, and we had 1 amp going through the blue, how much would be going through resistor 2? That current would be 2 amps because 1 amp plus 2 amps has to get you the 3 amps. So just kind of talking you through that logically, that's all it is. So it kind of makes sense. Again, if you think about water going through pipes, and if a pipe splits, part of the water is going to go one way, part of the water is going to go the other. And then if they come back together, when two pipes come together, whatever enters that junction should come out. So that's the junction rule. Again, if this happened to get broken, then this path is still an option. So this would still get powered by this battery, and the electricity would go through, and it would still work. So the rules for parallel circuits are these down here. So you got the total resistance, which is weird, so I'll talk about that in a second. Let me go through the other two first. So the total current is just the junction rule. So the total current is the current that goes through each, like the sum of the currents that go through each of the branches, so I1 plus I2. The voltages, if you think about the voltage, it's just the loop rule. So each individual, let me erase that. Each individual loop, so if we do a loop there, call that loop 2 because it's got resistor 2 in it, and then we could do this other loop here around there, and we'll call that loop 1. Each loop has to do the gain and drop rule. So if we gain whatever we gain across this battery, we're going to drop across resistor 2. And if we do the other loop, if we do the first loop here on this path, so if I gain across this battery, whatever I have gained across the battery, I'm going to lose against that resistor. So these individual voltages, if I measured the voltmeasure there or there or there, they're all going to be the same. And you should do that in that simulation lab and verify that for yourself. But that's just the loop rule here. And in parallel, the voltages are all the same. In the current, though, they add up. So these are sort of the reverse rules for series. And then this rule here is a strange rule, but that's the way that it actually functions. So if you imagine as you hook up more and more sort of resistors in parallel, so if I put another branch here and I got, ooh, that's really ugly. So if I put another branch in here and I stuck another resistor in, okay, we're basically opening up another path for electricity to come out of the battery and power that. So as we add more paths, we're actually adding more current in the circuit. And if you're keeping the voltage the same, so according to Ohm's law, the voltage equals the current times the resistance. If this is constant, constant value. And the current is increasing because as you open more paths for the electricity to flow, you're going to get more electricity. So that is increasing. So in order for that to happen, in order to keep this value constant, if you're increasing the current, the resistance has to decrease. So this is a weird effect, but it's actually what happens. So it decreases. So the total resistance decreases. So that means as you add more and more resistors in parallel, you get less effective resistance, which is a very strange, kind of counterintuitive idea, but it's what works. So, and to calculate the total resistance, it's a little bit funny, but we'll go through an example in a second. It's 1 over R1 plus 1 over R2. So you're kind of inverting each of the values for the resistances. You add them together, and then you raise it to the -1 power. So that's what you have to do in your calculator. So just to go through junction rule, and then we'll get into the practice. For the junction rule, at any junction, the sum of the entering currents should equal the sum of the exiting currents. So we talked about that a little bit. Here's an example with some diagrams. So if I look at this, the total current coming out of the battery and then going through this 80 ohm resistor is 1.25 amps. So it's going to get to this point, which is our junction, and it's going to split. So if 1.25 is sort of going this way, some of that current is going to go, through this path and around and back. So that's what we measured here as 0.25. And other part of the current would be going this way. And that was 1. So again, it sort of makes sense in terms of just our general rule here that we had 1.25 going into the junction, 0.5 going along the green, and 1 going on the blue. So if you add those two together, you get 1.25. It's conservation of matter idea. So let's try one that you're actually going to have to ponder a little bit. So given the pictures, determine the current through the 10 ohm resistor. So we're going to try to find the current in this one here. And the voltage and power across each one. So we're going to try to solve for the voltage and the power for each. And that's a little bit of practice of some of the stuff we did last time. So if you look at these diagrams, we got 0.6 going that way. We got 0.4 going that way. And the total, it looks like the total when it comes all back together and gets back to here, it looks like it's 2.2. So if we kind of set up our junction rule or the current rule with this, which I already did, so I'm going to just delete it. It's the current in the 20 plus the current in the 30 plus the current in this 10 should equal the total current. And there's a typo there, but that's okay. So 0.6 plus 0.4 plus whatever this current is in this section, which is what we're looking for, should equal 2.2. So if you just do the math there, you get 1.2 amps for that current. So we found the individual currents. We know the individual resistances. So voltages are just using Ohm's law, and the power equation for power would be P equals IV. So I'm just going to kind of show you how this all works out for each one individually. So if we look at the 20 ohm resistor, it'd be 0.6 because that's what we said the current was in the 20 times that resistance, which is 20. So 0.6 times 20 is 12 volts. So we have 12 volts across this piece here, and that's equal to the voltage of the battery. So that should make sense because they're parallel, right? These are all parallel and they're hooked up to a battery. So the battery voltage should be the voltage of each individual piece. For the power, it's just the current times the voltage. So the current is 0.6. We got that here. It's given. The voltage we just got is 12. So 0.6 times 12 is 7.2. Similar work for the 30 ohm, just with different kind of numbers or values. But it still works out that the current, which is 0.4 times the resistance, which is 30 in this case, gets you 12 volts. So that makes sense. Again, the voltages are the same in parallel. For the power, you just do the current times the voltage. So 0.4 times 12 is 4.8 watts. So they're a little bit different in terms of the power, but the voltages are all the same. And they're different in the power because they have different currents. So the one with more current is going to get more power. Finally, for the 10 ohm, again, very similar work, just substituting in the values for that. So we just calculated 1.2 amps for the current in the 10. The resistance is 10, so 1.2 times 10 still gets us 12. So that's a good kind of check that these are all equal for the voltages, because that's the rule for parallel, that the voltages should be all the same. If I did the power here, it'd be 1.2 times 12, which is 14.4. Just to check that, we could do the total power. So the total power would be the total current times the total voltage, so I did that over here. So 2.2 is the total current, because that's what we measured, or if we add up all the individual currents, we get 2.2. And then if we multiply that by the battery, you get 26.4. And if you just wanted to check, you can verify that if you add these three powers together, you get the total power. So that's the only way it works out for that, and it should just be, you know, using your VIR equation, V equals IR, and your PIV equation, P equals IV. So let's go through one where you have to actually calculate the resistance. So I'm just going to talk you through it. Let me check the time. We're at 10 minutes, so I'm going to try to go pretty quickly here. So 9-volt battery is hooked up to those 4 resistors that I have there. It tells you the individual resistances. Find the total resistance, the total current, and the voltage across, and the current in each. So we're just using that resistance rule. So the resistance rule, 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4, because we have 4 that are parallel. And then that sum added, or all that raised to the -1 power. I would just use the -1 key on your calculator, or the inverse key, or it might be a key that says like 1 over X. That would work. Either one on your calculator will make it easier for you to do this math. So it'd be 1 over 2 plus 1 over 4 plus 1 over 5 plus 1 over 7, and then you're going to add all those up in your calculator. I would just get them as decimals and add them, and then raise to the -1. When you do that, you get 0.915 ohms. So again, the more resistors we have, the lower the resistance, which is counterintuitive again for parallel. So then you can we found the total resistance, total current, we know the total voltage and the total resistance, so we're just going to use Ohm's law. So if I get rid of that, Ohm's law, V equals IR, so I'm using the total subscript, so 9 equals I, and then 0.915 is my resistance. So if I divide 9 divided by 0.915, you get 9.836. And if you, depending on how much you round, you'll get a couple more digits, but I just stopped there. We already know the voltage of each piece because in parallel, all the voltages are the same, so they're all 9 volts. And then it's just doing Ohm's law for each one to solve for a current. So 9 equals I1 times 2, which is the resistance of the first resistor. So you get 4.5 amps, and you would just repeat this process, 9 divided by whatever the resistor individual value is to get the individual current. And if you do all that, you get these values over here. And again, to check, they should all add up to the total. So that's our total. That when we add all those up, we get the same value. So we know that we did it correctly. So hopefully that's a pretty good model, so you can go through and practice and get an okay score on your electricity practice. So one more video to come, which is the electricity review, and then I think that should be about it. So have a good one, guys.